Hello! In this video, we are going to prove the following theorem. Suppose G is a group with identity element E, and suppose A and B are elements of G with finite order, and they commute. If the intersection of the groups generated by A and the group generated by B consists only of the identity element, then AB has finite order, and the order of AB is equal to the least common multiple of the orders of A and B. Now, a property of group elements that commute is the following. Given that A and B are group elements that commute, we have that AB to the power of n is equal to A to the power of n times B to the power of n for all integers n. And another property, which involves elements with finite order, is the following. Given that A is a group element with finite order and k is an integer, then A to the power of k is equal to the identity if and only if the order of A divides k. Okay, so now let's get into proving this theorem. Now for convenience, we're going to say that the order of A is equal to P, the order of B is equal to Q, and we're going to say that R is the least common multiple of the orders of A and B, which is equal to the least common multiple of P and Q. Now, since R is the least common multiple of P and Q, well then, R is a multiple of P and Q. Or in other words, we have that P divides R and Q divides R. Now, since P divides R, this means that R is equal to P times some integer. I'll call that integer I. And this means that R is equal to Q times some integer. I'll call that integer J. Now the whole goal is to show that the order of AB is equal to the least common multiple of the orders of A and B. Or in other words, we want to show that the order of AB is equal to R. And to show this, we want to show the following. We want to show that AB to the power of R is equal to the identity, and we want to show that R is the smallest positive integer that has this property. In other words, we want to show if lambda is any positive integer with the property that AB to the power of lambda is equal to the identity, then R is less than or equal to lambda. Okay, so let's first show that AB to the power of R is equal to the identity. Now first, since A and B commute, we know that AB to the power of R is equal to A to the power of R times B to the power of R. But then we're going to replace the first R with Pi, and we're going to replace the second R with Qj. And then by properties of exponents, A to the power of Pi is equal to A to the power of P to the power of I, and B to the power of Qj is equal to B to the power of Q to the power of J. But then, since the order of A is equal to P, we have that A to the power of P is equal to the identity. And since the order of B is equal to Q, we have that B to the power of Q is equal to the identity. So this is just equal to the identity to the power of I times the identity to the power of J. But the identity to the power of any integer is equal to the identity. So this is just equal to the identity times the identity, and by definition of the identity element, the identity times the identity is equal to the identity. So this shows that AB to the power of R is equal to the identity. But now we want to show that R is the smallest positive integer that does this. And to do that, let's suppose we are given an arbitrary positive integer, lambda, with the property that AB to the power of lambda is equal to the identity. To show that R is the smallest positive integer with this property, we want to show that R is less than or equal to lambda. Now, since A and B commute, we know that AB to the power of lambda is equal to A to the power of lambda times B to the power of lambda. So we have that a to the power of lambda times b to the power of lambda is equal to the identity. Now notice, if we take this equation and multiply b to the power of negative lambda on the right side of both of these expressions, we're going to get a to the power of lambda is equal to b to the power of negative lambda. And if we multiply a to the power of negative lambda on both sides, we get b to the power of lambda is equal to a to the power of negative lambda. So then what does this tell us? Well, we know that a to the power of lambda is a to the power of some integer. So a to the power of lambda is an element of the group generated by a. But this tells us that a to the power of lambda is also equal to b to the power of some integer. So that tells us a to the power of lambda is an element of the group generated by b as well. So a to the power of lambda must belong to their intersection. And we know that the intersection consists only of the identity element. Similarly, we know that b to the power of lambda is b to the power of some integer, so b to the power of lambda is an element of the group generated by b, but this tells us that b to the power of lambda is also a to the power of some integer, so b to the power of lambda also belongs to the group generated by a. So b to the power of lambda must belong to their intersection. And so this tells us that a to the power of lambda must be equal to the identity element, and b to the power of lambda must be equal to the identity element. But then by the second fact we have written here, this implies the order of a divides lambda, and this divides the order of b divides lambda. Or in other words, p divides lambda and q divides lambda. And this tells us that lambda is a common multiple of p and q. But r is the least common multiple of p and q, so r must be less than or equal to lambda, right? R is the smallest positive integer with this property. So since lambda is a positive integer with this property, r must be less than or equal to lambda. And so we've shown if lambda is any positive integer with the property that ab to the power of lambda is equal to the identity, then r is less than or equal to lambda. So that tells us that r is the smallest positive integer with the property that ab to the power of r is equal to the identity. So the order of ab must be equal to r. And r is the least common multiple of the orders of a and b. And that is exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.